Okay, so the next one is 63. In this one we have the alternating group A8, and in it we have to find a non-cyclic subgroup of order 4. So let's see the solution. Consider this subset. Say K, consisting of the identity element, then this product of two disjoint transpositions, that is two cycles, 1, 2 and 3, 4. Then another such 5, 6 and 7, 8, and the product of all these transpositions that you see here at once. Subset of A8. Because we have 8 symbols, so that's why these permutations in fact are in S8, in the actual symmetry group of degree 8. But at the same time, note that all of them are even permutations. Why? Because each one of them identity is of course an even permutation, we already know that. But the others are, each one of the others is a product of an even number of transpositions. So that's why by definition these three are also even permutations, and as such all of them actually belong to A8. So K is a subset of A8. Now one can verify that K is closed under multiplication, where you of course know what we mean by multiplication. It's the product of two permutations. So this one can routinely verify. You just have to see that this is the case. And that is why by the subgroup test, K is a subgroup of A8. Note that this is because we are working with a finite subset of the group A8. In fact, A8 itself is finite, so it's just enough to see that the subset in question is closed under multiplication or closed under the binary operation that you have in the group. You don't need to verify that inverses also exist. Inverses of the elements in K exist within K. Just finiteness and being closed under the product is enough for K to be a subgroup of A8. Thus, K is a subgroup of A8. Now, how do you know that this is not cyclic? And this definitely has order 4, that also we can see. Let's in fact mention that also. But why is it not cyclic? That's because it has no element of order 4, and as such it cannot have a generator that generates the whole subgroup. And why is that so? That is because the identity of course has order 1, and the other elements, each one of them has order 2, since the order of every non-identity element of K is 2, K is not cyclic. So that is our solution. Next, 64. Compute the order of each element of the alternating group A4. What arithmetic relationship do these orders, that is the orders of the elements, have with the order of A4 itself? Now we know that because in any symmetric group, the order of an element ultimately depends on the cycle structure of the element, that is, how it is a product of disjoint cycles. Depending on that, the order of the element can be determined, and it also does not matter exactly what cycles are involved. Actually, only the cycle lengths matter. So that's why we do not need to know all the elements of A4. We already know there are only 12 elements in A4, but we don't need to know all the elements. We just need to know what the cycle structures are, different cycle structures are that the elements of A4 possess. So we write the solution like this. In the beginning itself, we can of course settle the case for the identity element since its order is 1. The order of the identity element is 1. In every group, the order of an identity, whatever identity the group has, it is 1, and it's the only element of order 1. The order of the identity element is 1. Next come products of two disjoint cycles. Okay, because that means 4 symbols are involved. Say for example 1, 2 times 3 comma 4, and that is allowed here because we have only 4 symbols, and each such element would have order 2. That is because those disjoint cycles individually would have order 2, and you have to take their LCM. LCM of 2 and 2 is 2. So the order of a product of two disjoint cycles is 2. What other kind of cycle structure is possible in A4? Keep in mind that we also have to maintain the fact that the elements we are considering actually are even permutations, because A4. So any element of this type is actually in A4 because it's a product of two disjoint cycles or two disjoint transpositions, and that number 2 is even. Then we can of course also consider the 3 cycles of length 3, because 3 is odd, so as a permutation the cycle is even. The order of any why am I writing it like this? The order of any 3 cycle is 3, of course. The length of the cycle is its order, and a 3 cycle is also an even permutation due to its odd length, and hence it's in A4. And these things where we are mentioning products of disjoint cycles, we are not again explicitly mentioning that all these things are happening in A4. That is understood, and that's just it. There is no other type of cycle structure. What about a 4 cycle? 4 cycle, of course, is there will be several 4 cycles, but any 4 cycle, although it's an element of S4, it is not an element of A4 because a 4 cycle is not an even permutation. Why is that so? That is because the length is 4, which is even, so the permutation is odd. So we have in fact now found all the possible orders 1, 2 and 3. These orders all divide the order of A4, which is 4 factorial divided by 2. 4 factorial is the order of S4, the entire symmetric group of degree 4, and A4 is half of that. That means 24 divided by 2, so this is 12. 1 of course divides 12, 2 also divides 12, and 3 also divides 12. So that's just it. Next, show that every element in the alternating group AN for n at least 3 for n at least 3 can be expressed as a 3 cycle or a product of 3 cycles. Another way of stating this claim is that all the 3 cycles in Sn, where n is at least 3, generate An. In other words, to be more specific, if you collect all the 3 cycles in the entire symmetric group Sn and consider the smallest subgroup of Sn containing all those 3 cycles, then that is An. That's what we mean when we say that they generate An. And this in fact has already been solved in one of my videos. So I will just give you the URL as a solution. It has a title also, of course. It is this. Permutation groups, and this is part 7. Herstein. You already know how I name these videos. So in Herstein's group theory playlist, in that playlist you have this, and this video is not a very old one. Okay, so you can see that in this one we solve only 2 exercises. One of them is this, the one that comes after the first exercise in that video. However, for your convenience, let me just actually write the URL in its entirety. The first part is of course your usual youtube.com, and then you have that watch, followed by question mark, then v is equal to, yeah, this part is okay. Let me just carefully write what we have here. You do this only if you fail to find this video. You just go to that section where you have all the videos. You don't need to in fact go to playlist also, and you see that after say 5 or 6 videos which are the latest videos, you have this one. But still F9 UKD without any space, okay, UKDP capital R capital T capital N followed by 0, not O, then capital E ampersand AB underscore, then channel equal to a mathematical rule, and I will give you the timestamp also. there is no gap. A is capital, M is capital, R is capital, the rest are small letters. And the timestamp is this: at 43 minutes 26 seconds. I mean around this is where that solution starts. Okay, so you can just check this out and see. If you are still unable to follow, then of course you let me know. We then move on to the next one. There is no point repeating these things again and again, these solutions. So I thought, why not direct you to that part where it's already available, and that too not elsewhere but in my channel itself. Then the next one is this: show that for n greater than or equal to 3, the center of the symmetric group of degree n, Z of Sn or Z of Sn, is the trivial subgroup consisting of only the identity. Here is being denoted by epsilon or E. You can in fact use any letter you want. That means all the symmetric groups starting from the degree 3, 1 have trivial centers. So let's see how that can be proved. Let n be greater than or equal to 3. N is an integer at least 3. Now, what do we need to prove here? We need to prove that no non-identity element in Sn can belong to the center. In other words, no non-identity element in Sn can commute with all the elements of Sn. That means if we choose any non-identity element in Sn, we have to be able to show that there is some element in Sn with which it does not commute. So that will prevent it from being in the center of Sn, proving that the center only has the identity element. And of course, the identity element does commute with all the elements. That is true not just in Sn but in fact in any group. So let us start like this. Let sigma be an element in Sn such that sigma is not equal to, let's follow this symbol what the author has written. By epsilon we mean the identity element in Sn. So sigma is now a non-identity element. That means what? And what is the identity element here, by the way? That is the identity function from the set of all n natural numbers or n positive integers, to be more specific, onto the set itself that does not change anything. Okay, it sends 1 onto 1, 2 onto 2 and so on. So sigma is not equal to that. That means sigma does change something. So because of that, we will now have then there exist distinct symbols I and j, say, in this set such that sigma of I is equal to j. such that sigma of I is equal to j. Since n is greater than or equal to 3, we can further choose a symbol k in this set that is neither I nor j. Why is that so? That is because we have at least 3 symbols. So if in fact in the smallest possible case where n is 3, you still, after choosing I and j, or after getting I and j from here due to the non-identity nature of sigma, you still have one more option left for you. So that can always be chosen k, which is different from both I and j. Now let tau be equal to k. Tau is going to be the transposition. It's the transposition k comma j or j comma k, anything. These two are the same. So j comma k. Then what happens if we evaluate the composition of sigma and tau at I? So this just means sigma of tau of I by the definition of composition. I is different from j. Why? Because distinct symbols. I is also different from k because already k has been chosen in such a way that it's different from both I and j. So that means tau does not involve the symbol I. What that simply means is that tau does not change I. Tau keeps I fixed. Tau only changes among all these symbols that are available to us, all the n symbols. Tau changes j to k and k to j and keeps everything else fixed. So among those things, I mean other than j and k, I is also one such symbol, so tau will fix I. So tau of I is equal to I, and sigma of I is of course our j. But if we on the other hand calculate tau composition sigma at the input I, what do we then get? We then get tau of sigma of I, and sigma of I is j, and tau of j is what? Tau of j is k. And these two things are not the same, because one calculation gives us j and the other one gives us k, and j and k are distinct. So this is equal to k. Since j is not equal to k, that means this function sigma tau and this one tau sigma differ at I, at the input I at least. It may differ at other inputs also, but whatever the case is, we have shown that they cannot be equal as functions. Sigma tau not equal to tau sigma. So that element that we were talking about a while ago, that we should show that there is at least one element in Sn with which sigma does not commute. Tau is one such element. So that just simply means that sigma does not commute with all the elements of Sn, and as such it cannot belong to the center of Sn. And tau, of course, it definitely is an element of Sn. This shows hence no non-identity element can belong to the center. So the center has only the identity element. It's trivial, and all of these things are possible. They have become possible because n is at least 3, so that we have been able to choose one such k. In S2 that is not the case. I mean, choosing k is not possible. That's what I am saying. That's not the case there. So that's just it. Let me just end the video here itself. We are going to solve more in the next Gallian update about group exercises. And tomorrow, of course, we are going back to analysis. Last Sunday, something happened. Okay, I was not able to concentrate properly, so I just left it there. But tomorrow we are going to continue. We are right now doing countability, of course. So we are going to see next what type of things come. So with that, I wrap things up for tonight. So see you tomorrow with analysis. Until then, have fun with mathematics. So this is me, Lucifer from a mathematical room. Have a nice night.